All right, so let's start this problem. We want to draw the shear force and bending moment diagram. So I'm going to start by finding my beginning value. So I know this is positive shear at A. I'm assuming positive shear at B. I know my moments are going to be 0 at A and 0 at B. So if I find these reactions, that'll give me my starting place. We're not going to deal with this triangular distributed load directly. We're going to use the concentrated equivalent version. So what is the concentrated equivalent force? It's the area of the curve. It's a rectangle, triangle, 1/2 base times height. Should be 36. And what's the distance from A to that point? Should be 2/3 the distance, which will be 12. Right? So with that information, we should be able to find the reaction. So I'm going to come over here. I'm going to assume right-hand rule for my moments. And I'm going to sum moments about A. Make sure it's in equilibrium. So both the 36 kip force and my shear at B are acting down. So they're going to create what kind of moment about A? Negative. So the first one will be 36 kips. Its moment arm is 12. And then minus the shear at B, and its moment arm is 18. So it seems the shear at B is 24, negative 24. Is that okay? You got that? So now we're going to sum forces in the y direction. Again, assume up is positive. Define our shear at B. So I have shear at A acting up, shear at B acting down, and my 36 kip equivalent force acting down. So the shear at A turns out to be positive 12. Does that work? Okay. Any questions about that? So let's go ahead and draw the shear force and bending moment diagram. So I'm going to extend my template down on both sides. Oops. And as it stands right now, I don't have any point in the middle that's interesting to me right yet, so I'm not going to worry about it. I'm going to go ahead and establish positive x-axis, positive axis for my shear, indicate my units are in kips. So starting at the left side, what's my shear at A? We solved for it. It was 12. Positive. Now don't forget, our governing principles are that the change in shear is the area under the load curve. So what's the change in shear will be from over the whole length of the beam, 18, is the area under the load curve, which we've already found is 36, and it's negative. So 12 minus 36 brings me to 24. Negative. And you see that matches what we calculated the shear at B. So that makes me feel good. Now, what is the slope? Well, we know that the slope of the shear diagram is equal to the load. So what is the load? The load starting at A is 0. And it progressively gets larger to the end. In fact, that particular slope at the end is minus 4 to 1. So that means my curve has to fit between those two things. Let's see if I can do this well. Close enough. Uh-oh. What happened here? we cross the axis. This is going to be an interesting point for us later on. How do I find that value? Let's go back and use my relationship. So the change in shear between here and x1 is how much? Well, I start at 12 and I end up at 0. So my change in shear should be negative 12. Okay? If I extend this up, the area under the curve would be this part. So what is the area under the load curve? Well, it's a triangle, right? And it's going to be 1/2 the base times the height. What's the base? x1. What's the height? Well, I just need to know the slope of the line, right? What's the slope of the line? 4 over 18, which is basically 2 over 9. So this is going to be 2x1 over 9. Sorry? That'll be the value right here. At any cut x1, at any distance x1, the height should be 2x1 over 9. Does it work? When x is 0, what do you get?
0.
When x is 18, what do you get?
4.
It matches. So therefore, my area of the curve is going to be 1/2 base x1 times height 2x1 over 9. So these two things are equal. So I get minus 12 is equal. So the 2 cancels, and I get x1 squared over 9. So what is x1 equal to? It'll be 108. What's the square root of 108? 10 point something something. Tell me what the something something is.
39.
What?
10.39.
10.39? Let's make it 10.4. How about that? Everybody see that? Exciting, isn't it? I'm so glad I came to class today. All right. So, there's my positive moment, positive x-axis. This will be in kip feet. So what is the moment at A? 0. What is the moment at B? 0. This is going to be fun. What's the change in moment? Is the area under the load diagram. What's the area in the load diagram right here? Wow. Okay. One thing that's going to help us here is, since this has a 0 slope, this is a parabolic section. So if you look in your book, that little piece right there, the area is 2/3 the base times the height. So in our case, the base is x1, which is 10.4, and the height is 12. So what's that value going to be? That would require a calculator. I can't Rain Man these.
83.2.
Anybody else get 83.2? All right, it's all coming in now. It's raining 83.2. And it's positive. What's the shape of the curve? Well, remember the slope of the moment diagram is equal to the shear. So go up to the shear here. It's positive 12, decreasing to 0. So I know this is 0 slope, and this is a large positive slope. So I know that this part of the curve looks something like that. Now here's where our graphical process breaks down. I know the change in moment over this last section of the curve is this area. Anybody happen to know what that is off the top of their head? No. Neither end has a zero slope. That is not a spandrel or a parabolic section. It's just a chunk of a curve, which I don't know off the top of my head what it is. So you'd actually have to go back and find the equation for the shear and integrate it to find out. Now, I can tell you with some confidence that that area is negative 83.2, and it will bring you back to zero. But I cannot prove that to you with the information on this page. So that's where this graphical technique breaks down. When you are unable to graphically find areas under segments of the curve quickly, then you can't do it anymore.
With a quadratic, we can do like the full triangle and do like 2/3 of it.
No, that only counts for this part. Because that is a parabolic section. See, you have a zero slope. So that is truly a section of a parabola with the focus or the line of symmetry of the parabola is right here. Over here it's not. It would be hard to figure out. It's possible, but you probably don't want to deal with it. In fact, I'm just thinking you probably could figure it out, but I don't expect you to do it on the test. Now, on homework, you're sitting there with lots of time and resources. It would not be hard to figure out what the shear curve is. Then you would just integrate it, evaluate it, and you know the change in moment. But I'm pretty confident that's the value. And you can see the slope would start at 0 and go to a pretty large negative value. In this case, 1 to minus 24. And the resulting moment diagram would look like that. But you still have identified the maximum moment and where it occurs. Where is the maximum moment? Or what is the maximum moment? It's 83.2 kip feet. And it's at, what was that number we got? 10.4 feet from A. Right here. Any other questions? So I kind of wanted to end this section showing you the limitation of the graphical technique. All right.